I'm Caleb Walcott, and I'm a PhD candidate at the University at Buffalo in the geology department. I was, destined to be a polar scientist. I was born in Alaska, and although I grew up in Oregon, I spent summers often going back and visiting my grandparents there. And I noticed, from a young age that glaciers there were changing within my lifetime, and that was shocking to me. It got me thinking, if this is happening here in Alaska and the States, what's happening at the poles? What's happening in Greenland? What's happening in Antarctica? What's going to happen in the future? So those formative experiences when I was a kid really got me interested in polar science, and it's been drawing me in ever since. Broadly speaking, I'm a glacial geologist. I study areas that were once covered by ice sheets, including here in western New York and parts of southeastern Alaska. I study areas that are currently covered by ice sheets that have evolved in the past, like areas right next to the modern Greenland ice sheet. And I'm really interested in how these glaciers and ice sheets have evolved over the past maybe 250,000 years or so, right? And understanding how they've responded to climate and how this might inform how we understand how glaciers will evolve in response to future climate change. So glaciers and ice sheets grow and shrink in response to climate change. And glaciers are also really good at eroding and moving materials. So this means as the glacier grows, it'll bring with it anything from tiny pieces of sand to boulders the size of cars and even houses. And when these glaciers, they grow, they bring this material along, and then when these glaciers retreat and begin to melt, it drops these materials as, across the landscape, and these serve as markers of the past extent of the glacier. And so if we look at the landscape today and we can map out, these big boulder deposits or all these sediments, these are footprints of how big the glacier or ice sheet was in its past. And while these footprints are really cool to see, right, because they tell us that glaciers and ice sheets were bigger in the past, it's really important to figure out how old these rocks are, like how long they've been on the landscape, to figure out when exactly ice sheets and glaciers were in the past. Because once we know when they were bigger in the past and how they've retreated over time, maybe how quickly they've retreated, how long it took them to retreat, then we can contextualize these in regards to climate change and use this information to try and predict how glaciers and ice sheets will evolve in the future. So in the past, there have been glaciers and ice sheets all over the world. Places, such as Hawaii had glaciers. Here in Buffalo, New York, we were covered by an ice sheet. Greenland, Antarctica, of course, most of Western Europe. And so there's markers of past glaciers and past ice sheet change all over the world. And so that allows me to travel a lot for my job, which is the favorite part of my job, right? Is getting to go to these really cool, interesting places and conduct field work. In the past, I worked a lot in southeastern Alaska, and today I work mainly in Greenland and also here in my own backyard here in western New York. So what we do when we go to the field is we look for boulders, right? We're looking for things maybe 3 feet by 3 feet by 3 feet, if not bigger. I've seen boulders the size of pickup trucks. I've seen boulders the size of houses. So the sky's the limit on these sizes, really. And so what we do in the field is we go at these rocks with a hammer, a chisel, and a rock saw. And what we're really trying to get is about a kilogram or a softball size of rock to bring home back with us to the lab, so we can figure out how many of these cosmogenic nuclides are in them.
Cosmic rays come from events in space, such as supernova explosions. These rays strike gases in the atmosphere. Secondary rays are emitted. These secondary particles strike rock. Atoms in the rock, such as oxygen-16, are altered. Beryllium-10 builds up over time. As glaciers grow and shrink, they move around lots of material, including large boulders. These boulders are dropped as the glacier melts, and they begin accumulating beryllium-10 when they are exposed to the atmosphere. Therefore, I can walk along the line where a glacier retreated in the past and measure the amount of beryllium-10 in the boulders and figure out when the glacier retreated to that point and how fast it was retreating. When ice re-advances over a surface that has been exposed to the atmosphere for a long time, beryllium-10 is no longer produced. Beryllium-10, however, is radioactive, and over time this beryllium-10 decays away. Scientists can sometimes look at the amount of beryllium-10 left in rock surfaces that were covered by ice to figure out how long ice covered that area.
So when we're in the lab, we take these rocks, about this softball size, and first, these rocks, we really beat them to death. First, we crush them, to separate them into stuff that's about the size of sand that you might find at the beach. Then we hit them with a bunch of acid to remove some impurities. Then we put them through what's called density separation to separate the mineral quartz from all the other minerals. And then we just leave them in hot acid baths for days, if not weeks at a time, just really trying to get the cleanest quartz possible. And once we have this really clean quartz, we do a lot of relatively complex chemistry where we're trying to isolate these certain cosmogenic nuclides, right? Whether it's beryllium-10 or aluminum-26 or radiocarbon, it takes a lot of work to only take out these elements and leave everything else behind. So once we've got this beryllium or this aluminum or carbon extracted and isolated, we pack these into little metal targets and we send this off to an AMS or an accelerator mass spectrometer facility where they count on these really big instruments how many individual atoms of beryllium or aluminum or carbon there are. And so they send this number back to us, right? And this is where the fun part begins. This is where we say, okay, we have X number of beryllium atoms. What can this tell us about how long this rock was here on the landscape? And what does that tell us about ice sheet history?
This is a plot of the decay of beryllium-10 radionuclides. You will notice that it takes a long time to decay. In fact, it takes 1.4 million years for half of the materials to decay. An exponential function is a function that represents this decay. N0 represents the amount of starting material, E is a constant seen a lot in the natural world, lambda is a decay rate determined by the material, and T is the amount of time. N represents the amount of materials left at the end of the time period. For instance, if you start with 1 million atoms of beryllium-10, a million years later, you will have about 600,000 beryllium-10 atoms left. Beryllium-10 is a really great tool, but we often don't know how much beryllium-10 we start off with. Therefore, geologists use lots of different nuclides to figure out how long a surface has been buried or exposed. Fortunately, there are other atoms that are similar to beryllium-10 and form in the exact same way through cosmic rays, and then they decay. One of these is the radionuclide aluminum-26. The constant that represents the rates is different for aluminum-26 than beryllium-10, so their plots look different. Another radionuclide that you might have heard about is C14. We need to zoom in for that one because it has really different rates from beryllium-10 and aluminum-26 and works really well over the windows of hundreds to about 20,000 years. Once again, the rate is different, so the plots look different. By looking at many of these different atoms, we scientists can compare their amounts based off these graphs and figure out how long a surface was buried or exposed. You can use the plots we have shown to find the time using the starting and ending amounts. But it would be easier to solve for t in the equation. This would allow us to avoid looking at the graph each time. We can rearrange the function, solving for t. This will give us a natural log function, the inverse of an exponential function with a base of e.